Welcome back to our third review video as we gear up for May 8th in the AP exam. Today we're going to tackle a very intimidating topic that pertains to interpreting graphs. Particularly what they might do is they might give us a picture of f of x and ask us, what f prime is going to look like, or vice versa. They might give us a picture of f prime and ask us, hey, what does the original function, the antiderivative, look like? And so we're going to try to develop a game plan for each of these techniques specifically, and then we're going to try to get lots of practice under our belt. So our first situation is we're going to assume that they've given us a picture of f, and who knows what it's going to look like. Maybe they're just going to give us a nice little parabola like this, so that would be very kind of them. The first technique that I always start with is find all horizontal tangent lines. Okay, look for horizontal tangent lines, look for moments where the graph might have a slope of 0. So we could say, right here at the turning point there's a slope of 0, and what that's going to do is that's going to correspond to a point where f prime has a root. So we'll say whenever f has a slope of 0, that implies that f prime is going to be having a root or an x-intercept, or it's going to be crossing the x-axis, however you want to say it. The second thing we want to look for is an interval where f of x is increasing. So on this particular parabola, I said, okay, that entire interval, whenever x is greater than 0, the function's increasing. So basically, whenever f is increasing, then that implies that f prime is going to be positive, aka above the x-axis. And then last but not least, we're also going to look for intervals where f might be decreasing. There's certainly no rhyme or reason to whether we do step 2 or 3 in any particular order. We've got this whole interval over here where f's decreasing, so of course whenever f is decreasing, then that corresponds to, or that implies that f prime will be negative, aka below the x-axis. So let's go try one. So we'll kind of pick up with the example we kind of had on the last slide, where they've given us a picture of f of x, very simple parabola, and as I get ready to try to sketch the corresponding derivative here, and I'll label a few points on the x-axis in each direction. So the first thing we said, we got to identify any horizontal tangent line. So I said, bang, right off the bat, right there, when x equals 0, we have a horizontal tangent line or a slope of 0. So I know that over here we're going to cross right through the origin, because when x equals 0, f prime has a value of 0. The other one we said, let's look for intervals of increasing. We say, okay, anytime x is greater than 0, we're increasing. So what's happening is, like for instance right here, I have a positive slope, but it's very small. And then we still have a positive slope, but it's bigger, and then the positive slope's even bigger yet. So what's happening is at x equals 1, we're positive, but not by very much. When x equals 2, we're more positive. When x equals 3, we're even more positive, because the tangent lines are getting steeper and steeper. Then we could also look for intervals of decreasing. In this entire interval right here, we're decreasing. When x equals negative 3, we're very negative. When x equals 2, we're not quite as negative. And when x equals negative 1, we're still negative, but not as much. So for instance, at negative 3, we were very negative. Negative 2, we're still negative. Negative 1, we were negative, but not as much. And so what we're starting to get is, we're starting to get a glimpse of what that derivative looks like. It's just a nice linear function. And a real neat secret, I guess, well, it's not really a secret, but a real tip here is always expect your derivative to be 1 degree less than what you started with. So if you're looking at the original f and you're thinking, wow, this definitely looks like a 2nd degree polynomial, then his derivative is going to be a linear function each and every time. So that's just kind of a general rule of thumb. Doesn't work for all pictures. They might not give you a polynomial, but if it's a polynomial, that's going to work every time. So we'll try another similar picture here. They've given us a picture of f of x yet again, and they want to try to sketch the derivative. So the first thing is we jumped all over. We said, you know what, really looks like there's a horizontal tangent line there, and we'll assume so for this particular problem. So when x equals 2, we know we've got the derivative crossing the x-axis, and that's the very first dot I want everybody to get on their paper instantly. Then we're going to look for intervals of increasing. Well, it looks like this particular graph happens to always be increasing throughout its entire domain. Just happens to be, when's it increasing the most, and so forth. So let's see, maybe if we said this is negative 2, and again, I'm just eyeballing it, so to speak, we're extremely positive right there. And then we get less and less positive. So for instance, at x equals negative 1, we are barely positive, just by a whisker. Whereas when we were back here at -2, we were really positive. And then it kind of mirrors that behavior on the other side. At x equals 3, barely positive. But by the time I get to x equals 4, 5, and so on, it gets more and more positive. So it kind of feels like we've got kind of a parabola developing here. And I think you'd all agree that if you did look at f of x, he looks like a third degree function, looks kind of like x cubed except shifted. So we're expecting the derivative to be a second degree polynomial, and that's why we've got a parabola. All right, the last one we do here by hand is going to be the most challenging one, of course, and you can see f is kind of a crazy looking function that's got vertical asymptotes at -3 and 3, and that's the first thing I want to stress, is that if the original function's not continuous at -3 or at +3, then the derivative automatically is not going to exist or be continuous there either. So we could just kind of paste and copy those vertical asymptotes instantly, knowing that this is going to take place. The next thing we're going to look for is we're going to look for horizontal asymptotes. Now there's actually not quite one here, although we do get very close there at the origin. However, it doesn't quite flatten out. It still has a slight negative slope to its tangent line right there. So what I'm going to do is I'm going to say, okay, we're just slightly negative right there. Now back here I say -2, -2.5, -2.9. We're extremely negative. So we're going from super negative to, slightly less negative, and then on the other side of x equals 0, we're going to start to mirror that behavior where the slopes are again getting very negative. And so within those asymptotes, I think f prime is going to look just like that. The other thing you'll agree is that this f picture is always decreasing, therefore my f prime is going to always be below the x-axis. And then the other parts here. This one's kind of interesting. This one, again, is always decreasing. You're slightly negative, more negative, and then even more negative. So it's almost going to be an exact replica as the original function, where the old y values kind of predict the slope over here. And then last but not least, we're very, very negative, slightly negative, and barely negative as far as the slopes go. So I'm going to kind of be a mirror image here. So we've got an even function that's symmetric with respect to the y-axis, and the biggest thing I want to stress is that derivative never, ever gets above the x-axis. Here's a great matching exercise here, and I would encourage you to, hit the pause button right now and try to match up these 5 pictures with their corresponding derivatives. On the left, you've got your original functions, and on the right, you've got their corresponding derivatives, and it's simply a matching game. And then, of course, you can come on back and hit play and see if we had kind of the same train of thought and the same reasoning behind our answers. Okay, welcome back, and let's see what we got. Let's see, the first one right off the bat, I knew I've got a horizontal tangent line up there. And so I'm looking for a graph that crosses the x-axis right at x equals 0, and it looks like the first two do. So I know that this one could be either A or it could be B. Now the next thing is we know we're increasing for a while, so I have to be above the x-axis entirely, and that's why I love this one. It looks like it kind of gets the steepest right about halfway, and that's what corresponds right up there. And then it starts to decrease, and that's why it's below the x-axis. So I think we've got a great match. I'm going to put B right here. Let's see, what else jumps out at me as being fairly innocent? Of course, we've got one here that's oscillating, so you expect his derivative to also oscillate. Right here where we've got a horizontal tangent line, that corresponds to a root, and so forth. So I think that was a fairly easy matchup right there. Let's see if we can change pen colors here a little bit. The third one, let's see. First of all, the derivative doesn't exist somewhere around x equals 1 or x equals 2, so that's kind of a giveaway. So it kind of looks like it could be D or E maybe, where the derivative doesn't exist. But certainly, if this bears decreasing, we want something that's below. And then again, this bears decreasing, so again below. And because this graph's never above the x-axis, I thought it was a really good match here with this one. Looking for, let's see if we can get a different color. Okay, next thing here we've got, looks like we've got 3 horizontal tangent lines all within kind of the same area. And you notice up here how we've got the 3 different roots, and that's because of those 3 roots. I matched it up down here, and I put A right there. And then last but not least, we've got a function that's not differentiable here at x equals 0, and that's why when you look at d over here, you see a derivative that's non-existent when x equals 0. We've got a constant slope here of -1 and then a constant slope of +1, and that corresponds to the -1 and +1 we see here, so we've got a nice match there. Okay, I want to switch gears real quick here at the end of this video, and we're going to say, okay, what happens if they give us f prime this time, and now they want us to sketch f? Well, here's the deal. When you're looking at that picture of f prime, find the roots right away. And look at those roots and try to determine whether f has a relative max or a relative min at that particular point. That's where you definitely want to start with, okay? Then we're going to find the intervals whenever f prime is above the x-axis. Now, when I say above the x-axis, I'm really saying positive, right? So whenever f prime is positive, then that implies that f itself is going to be increasing. And then last but not least, find out whenever f prime is below the x-axis. And of course, we're trying to really say negative. And whenever f prime happens to be negative, then of course that implies that f itself is now decreasing. So let's go try a couple. So here's a pretty funky looking picture. It's a picture of f prime. And so we said, all right, if we're going to attempt to draw f, the first thing we need to do is to figure out where the roots are on f prime. And so we said, okay, we've got a root right here, and at that moment f prime is changing from negative to positive. So we know that f's, I'm going to make a little note, we're going to have end up with a min there, -5. And then over here is another root, and f prime happens to be changing from positive to negative, so now we've got a maximum at -1. Now, there is a little freedom when you go to draw f. For instance, if there's a min at -5, and we'll try to scale this, it's -3, -4, -5. Where do you put the min? Well, as far as the particular height, we don't really know. You can put that min as high or as low as you want, as long as it's lower than, of course, the max. So I'm going to say, let's say my min's maybe has a height of 1, and then my maximum at -1 has a height of, say 5 or 6 or something like that. Now, the last thing we're going to talk about is, well, when f prime's negative, we're going to make sure that f's decreasing. So I might draw something like this. And then when f prime's above the x-axis, we need to make sure that f's now increasing. Round it off a little bit there. And then, of course, when the graph's below the x-axis, f's now decreasing. The other nice, interesting point that we should kind of talk about here briefly is this maximum point. Remember when f prime, when the slope of f prime changes from, say, positive to negative, that means f's actually going to have a point of inflection. So if f prime has a max at -3, then we need to make sure we've got a point of inflection here at -3. And it does look like, as long as we're careful, the graph changes concavity right then. In our last slide of the night, I want to introduce you to one of my favorite websites of all time. And the actual web address is kind of messy, but just go to Google and type in Big Derivative Puzzle. Alright, and you'll get a great website. I can't even remember which university to give credit to, but they've developed this applet that allows you to drag these pictures and match them up with each other. Now, the 4 pictures in the top row represent the original function f, and the 4 pictures in the bottom row represent f prime, and it's free and you can play it as much as you want, and it's just a matter of clicking and dragging, and they'll give you instant feedback to let you know whether you were right or not. So what I'm going to do is I'm going to leave you hanging here. I'm not going to match them up for you. I want to see you match them up in your notebook, and that'll give me something to kind of check tomorrow in class. So good luck with these, and we'll talk to you tomorrow.